The second presentation today is achieving multi-level CAN/FD security by complementing available technologies. This paper was written by Olaf Pfeiffer from Embedded Systems Academy and Andreas Walz and Professor Sikora from Offenburg University of Applied Sciences, and is being presented now by Andreas Walz. He studied physics and computer science at the University of Freiburg and joined the Institute of Reliable Embedded Systems and Communications Electronics, which is headed by Professor Sikora at the Offenburg University of Applied Sciences in September 2014. Since then, he is working as a research engineer in the field of communication security for embedded systems. He was involved in a number of research projects related to secure car-to-car communication, and currently his focus is on secure communications for industrial automation, and he is also a member of the security working group of the Profibus and Profinet International Organization. And now I'd like to ask you to start your presentation, please.
Okay, thank you very much for this very nice introduction. So this talk was actually supposed to be given by Olaf Pfeiffer, but for some personal reasons he's not able to give this presentation today. So I will give my best to be a worthy replacement of Olaf for the next 30 minutes. Maybe it's also important to mention that what I'm going to show here is a joint work between a number of people from Embedded Systems Academy, from NXP Semiconductors, and from our university, which is Offenburg University of Applied Science. So I think from the previous presentation, we have nicely learned that security is not just a product. It's not just like a magic elixir of which you can drop into your system and you will magically get security in that system. Security is rather a process which needs a number of considerations, and the important thing is I think that you need technology to achieve security. So technology is in some sense necessary, but it's not sufficient. So you need more than just that. Still, what I'm going to show you in the following is like a high altitude overview of different technologies that exist to achieve secure CAN communication. And by secure, what I mean is we have authentication, so we can ensure or validate who sent a certain message, who claims to be something or somewhat. We have integrity protection, so in the sense that tampering with messages can be detected. And optionally, we have encryption, so confidentiality can be protected. And additionally, which is I think also pretty important, is denial of service protection. And what I'm going to show you is that there are different technologies. They operate on different levels, and from this they also have different capabilities and limitations. And it's important to understand these limitations and capabilities, and also the related resource requirements, and also the implied costs, in order to make a reasonable selection of what to use. So now the question is, what actually does exist? We split this into 3 different categories as an example, and we're going to go through these 3 categories and discuss when to use technologies from these 3 categories. And I think the best way to have such a discussion is to give an example. And the example is here an elevator. So think of a building where there's an elevator, you have 4 floors, you have, on these 4 floors, you have respectively control panels with display and buttons potentially. They are all wired via CAN bus to the elevator drive. You have a central controller which is controlling everything. These elements build a CAN domain, and then we have a bridge element, something like a gateway, which connects to another second CAN domain, which is inside the cabin, which then connects different buttons, maybe sensors, door drives, and so on and so on. From the controller, we have potentially a connection to the internet for remote diagnostics, for example, and for local diagnostics, we have a separate CAN domain here, which is temporal, where we can have local diagnostics essentially. So this is now our example, and I mean, typical or possible attack scenarios are that someone taps the wires here, because I mean the control panels here. Sorry, that was too fast. The wires here, because the control panels can be opened, and you can easily get access to these wires and maybe attach new devices. You can think of remote attacks through internet access, for example, and also maybe kind of back-end attacks where something is attacking the infrastructure behind these remote diagnostics. So what are the available technologies? So maybe giving a brief overview. If we consider this here on the CAN communication layers, we have what is called ID guarding in hardware. We have ID guarding in software, which is, let's say, a low-level measure. We also have what we generally call a CAN crypto layer, and there are a number of different solutions to this. So cryptographic protection of individual CAN messages. And we have also something here, which is DTLS or TLS, which has been mentioned also in the previous presentation, which provides some kind of internet-grade security for CAN systems. So maybe let's quickly look into the ID guarding thing. ID guarding works by having something like allow or pass, and on the other hand, deny or block lists. And that means that within the transceiver, we have an element that either lets certain messages according to ID pass or not. And from this, we can actually achieve implicit authentication, because what is possible here is that if a message is injected, which is kind of spoofed, then the legitimate owner of this CAN ID can say, wait, this it wasn't me who sent the message, even though I actually own the ID, and can by this invalidate the message. This is the idea of ID guarding, which achieves implicit authentication without using any cryptography. And this is actually the very nice feature of this. However, one needs to consider that this does not work across CAN domains, because this invalidation done by such a transceiver cannot pass through the bridge. So it's only a local matter, and it also requires that there is always a corresponding ID guard transceiver, which is actually protecting the IDs that are used in the system. Another interesting feature of this ID guarding technology is that it can also protect against the own host. So if you have, for example, software issues on any of these host MCUs, the ID guard can also rate or prevent or have a rate limit on the message frequency, and by this can prevent, for example, CAN bus flooding. So in our example, we would, for example, use ID guard transceivers here for each of the CAN domains. So within each CAN domain for each of the individual elements, and by this we can have inside each CAN domain this kind of implicit authentication, and also the rate limiting. Now you can do ID guarding either in software or in hardware. And then, of course, there are different pros and cons for these different options. So for hardware-based ID guarding, for example, as I said before, you can essentially prevent also from a rogue host, because the host cannot really change the configuration of the ID guard transceiver. But of course, you have a limited number of filters in such devices. hardware ID guarding can be done on the transceiver level and also on the controller level, and both essentially have the same pros and cons in that sense. It's a bit different for the software ID guarding, in which case you would have an additional software component running on the host MCU, which would do the job. But of course, you can be very flexible then, because you can have a large number of filters potentially, but on the other hand, your reaction capabilities are limited, and also you cannot really prevent issues that are induced by the host or by an infected host. So this is certainly a limitation of software ID guarding. Now, the other or next category of technology is what we call CAN crypto layer, which is based on strong cryptographic measures. So symmetric ciphers, either in a lightweight form, and there's actually a bunch of lightweight cryptographic ciphers which can provide integrity protection and encryption. And I think the most famous is this AES, Advanced Encryption Standard cipher, which is also one option here to be used. But the baseline is that for these, you need to have shared symmetric keys somehow stored in the devices, which are then used to apply this cryptographic protection to the actual messages that you're exchanging. And of course, and this is also important to note, in contrast to the ID guarding, here in this case, you get additional overhead, because on the one hand, you need to do the cryptographic computations, for example, calculating cryptographic checksum. And on the other hand, you also need to transport this additional cryptographic data. So you really get overhead both on the computation side, but also on the bandwidth side, which is not the case for the ID guarding. There's one example of such a CAN crypto layer, but it's certainly not the only example, which is CANcrypt, which essentially provides a secure heartbeat mechanism, which allows a grouping of devices, and which then can inform each other on a regular basis that they are still present, that they don't have been tampered with, and in this way also update the symmetric keys that they are using for protecting the actual communication. But again, another drawback here is that you somehow need to get these initial shared symmetric keys into the devices. And considering again our example, one could do something like this. So in addition to the ID guarding, which I've shown before, you could have here, for example, CAN crypto layer implementations in respective elements that need to communicate securely across CAN domains, so through the bridge. And by this, you can essentially and potentially achieve end-to-end security between these devices, which is not possible with the ID guarding case. Okay, now the third category would be internet-grade end-to-end security with TLS or DTLS. So I'm pretty sure every one of you uses TLS essentially every day, because TLS is the transport layer security. It's standardized by the Internet Engineering Task Force, and it's the protocol that essentially runs HTTPS. So whenever you visit a website securely, which fortunately today happens in more than 99% of the cases, I would say, then you're essentially using the TLS protocol to get a secure connection from your local browser to the web server. Now, the nice thing with this TLS protocol is, even though it comes from this internet and web world and IT world where we have virtually unlimited resources, you can still use it in a way that it allows to be mapped onto smaller systems. And by this, you get a big benefit, because TLS is really, I would say, one of the most scrutinized protocols, security protocols out there, because it's so abundantly used that everyone is trying to get fame by finding flaws in the protocol. And by this, you have a lot of eyes looking into the protocol, looking onto implementations. And it's really a nice thing to benefit from this large community that ensures that TLS essentially in most cases works properly. Now, what you can do is then adopt this internet-grade security for CANopen FD networks using a variant of TLS, which is called DTLS, datagram TLS. That's slightly different from TLS in the sense that it does not require these reliable TCP-like channels, but you can have you can send the TLS or DTLS telegrams through channel that that may drop or reorder packets, and by this you get somehow a more robust use of this. And what TLS essentially is then providing, it provides data integrity and confidentiality. So whatever kind of application data you route through this TLS protocol gets strong integrity and confidentiality protection. And you also get endpoint authentication. And here you have a number of different options that you can use. So you can use certificates, which is, I would say, the large scale approach. You can also have pre-shared keys or passwords or whatever you want. And our approach is to somehow tunnel these DTLS datagrams through the CAN network, and then have a DTLS or TLS connection between, for example, if we go back to our example, between a local diagnostics and a controller system, because the local diagnostic system is something which is not permanently present, so ID guarding doesn't work. CAN crypto layer is hard because you need shared keys, and if this local diagnostic thing is hasn't been paired with this controller before, it's also hard to get this done with the CAN crypto layer. So DTLS would be one approach here, and it is in particular interesting to use it, for example, between remote diagnostics, where you have this remote diagnostics element down here, which connects through the internet, through the controller, which then routes the packets, for example, to one particular board, which is connected to CAN. And with this, you can achieve end-to-end security in the way that this remote diagnostics entity knows that it's talking to that particular board and vice versa. This particular board can ensure that it's talking to a legitimate remote diagnostics element. Okay, so we have prepared here, let's say, a first try to summarize the different technologies and their characteristics and properties. We have the ID guarding, again, the CAN crypto layer, and this TLS, DTLS for remote access. So I don't want to go through details of this table. I think it's probably more interesting for reference for you. The things that are mentioned here essentially have been mentioned before. Okay, now what remains is the question actually when to use what. So we showed that there are these three course categories of technologies, and the question is, when do you use what? And I think one thing that one should mention before is that if we had unlimited resources, we might probably use all the technologies as a stack, essentially. This would be kind of the brute force approach. We throw everything onto the system, what we have, and we hope that we achieve good results. However, I mean, it's also clear that the cryptographic elements require computational resources, require bandwidth. You have to do configuration of all these things. All these technologies come also with drawbacks mentioned before. So from an efficiency point of view, it's certainly worth considering somehow the best combination and not just the brute force approach. So maybe as some general recommendations, considering again the example that we've used, the elevator example. So first of all, your system should be designed in a way that dynamic IDs are not really used. So the CAN ID usage should not change during runtime, because this essentially would prevent the very interesting ID guarding approach from working properly. Then it should also be such that on a certain CAN domain, there should not be coming and leaving devices. So adding and removing of devices should be done through bridges or gateways, something that has a particular one-to-one connection to this temporary device. Again, because if devices are temporary, they cannot really be authenticated using the ID guarding thing. But if you consider this, then the next steps to take would be you should protect every CAN domain with ID guarding, because this is really let's say the baseline technology that helps you to protect from a large class of potential attacks with virtually no overhead regarding the computational resources and the bandwidth. Then considering the limitations, which on the ID guarding side is also that it cannot really cross CAN domains. Whenever you have communication that has to cross CAN domains, you should consider something like a CAN cryptographic layer, where you have really cryptographic protection using strong cryptography for the communication in a way that the security measure can cross CAN domains, can be routed through bridges, for example. And this essentially provides you with authentication on application layer, and it can also give you encryption, which means that if you have sensitive data sent through the network, which only certain parties should be able to read, then you should use encryption. This is also something which obviously CAN ID guarding cannot really provide. And then as a last recommendation here, whenever you have remote devices that are outside these CAN domains, potentially even connected through the internet, then you should use something like TLS or DTLS, something that really provides a one-to-one, end-to-end strong communication security, including authentication. This allows you really to have a strong assurance of authentic devices that are not permanently present, but maybe are something like drive-by devices. Now, putting all together, how would this look like in our elevator example? So as I said before, we would have ID guarding for all these internal CAN domains here, which would do this baseline protection of preventing message spoofing, for example, or rate limitations, so preventing host MCU from flooding us and doing some kind of denial of service attack. Sorry, that was not my intention. This would be the baseline. This would be used now for these internal CAN domains. Then additionally, we would consider this CAN cryptographic layer for communications, secure communications that need to cross CAN domains, like through this bridge here, for example. So we'd have something like this in the controller and in the drive element here, and then also in certain controllers within the cabin, for example. Oh, I'm sorry, there's probably some automatic timer, which I don't have under control. And last but not least, we would have DTLS here for this temporary local diagnostic element, which is only connected once in a while, and which then needs to do some strong authentication in order to ensure that no one is misusing this diagnostic interface. And also for remote diagnostics, for example, of this door control board here. I'm very sorry for this. To ensure this strong security in the communication between this remote diagnostic things and this board, as an example. But of course, you can also use this to diagnose or maybe firmware update other boards here. Okay, in order to show that what we proposed here, in particular, the DTLS thing, in order to show that this is not just academic paperwork, but really has practical usability, we built a demonstrator, which we showed, I think it was in 2019 on the Embedded World Conference, where we essentially built a demonstrator of a tablet, which is connected via Bluetooth to some gateway element, which is then connected via CAN to a number of devices. These CAN devices here in the middle, they essentially use the ID guarding to do this baseline protection. We have a CAN-crypt implementation between certain devices here, and we have the DTLS connectivity between the tablet and this controller shown here. And this DTLS connection is then routed through the Bluetooth interface, and then here through CAN messages, and allows us essentially to set up a connection, a secure connection, in a way that you can communicate with this controller here securely. Okay, coming to the conclusion. So I hope I was able to show you that there is a number of different categories of security technologies that can help you to implement secure communication in CAN systems. And just to repeat, there was this ID guarding, which is essentially almost overheadless. So it doesn't use any cryptography, but allows you to do CAN message authentication in some sense in an implicit way. We have the CAN crypto layer, which is always helpful whenever you need to have secure communication across different CAN domains where the ID guarding cannot really help. Or, for example, if you need encryption where ID guarding also cannot help. And additionally, we have this TLS or DTLS-based internet-grade end-to-end security usable through CAN networks, including the embedded and somehow limited resources in the end nodes to have really internet-grade security, strong authentication, potentially using certificates, but also other kinds of credentials are possible to have a measure whenever you have really, let's say, remote access through the internet or devices which are not permanently present, which come and go on a certain basis. And it should also have hopefully become clear that there is no silver bullet. So you always have to consider, and this is somehow again a link to the previous talk, you always have to consider the special characteristics of your system, the needs, the requirements, and then you need to consider which of these technologies to use in which sense. So essentially how to combine these technologies to get a reasonable, effective, and efficient security solution for your particular system. So thank you very much. That's all from my side, I think.